Let me pull up the lecture for today and you guys see that okay?
Yeah.
Okay. All right, we're going to start with talking about soil salinity. And let me change the display here. So soil salinity. This salinity is a word that refers exclusively to the total salts in the soil. And I don't know if you've ever been around a place where you get areas of white patchiness like this. This is like an extreme example of something that's got just a ton of salt in it. It's actually kind of weeping up this fence post here. And we do have areas like this around in eastern Washington. Generally speaking, they're found kind of in low-lying areas, but we do get some salinity issues here and there. Now, the sources could be a number of different things. Number one, and probably the biggest one, is parent material. So if you've got something that's in close contact with marine type rocks or minerals that are high in salts, those can be a source of salinity. Another one is oceans, and lastly, topography. And basically the idea of topography is that crap moves downhill, right? So if water moves downhill, nutrients tend to go with it. And nutrients for plants are salts, okay? And so as those things move with the water, and let's say they hit a low spot and there's nowhere for them to go, that's where they tend to collect generally. So topography is a big one, especially around here. You know, a lot of this ground was irrigated with rills, and even today it still is. But rills operate under the premise that water is, you know, slowly moving downhill. And as it does that, it takes salts with it. And so generally what you'll find is that in real irrigated ground at the very, you know, bottom of the field, that's where everything kind of collects. That's where it tends to be the most salty. So these are, you know, basically salts are any cation or anion. Okay, we've talked about these quite a bit. They can be associated with any or all of these different anions. And when things are dissolved in water, either cations or anions, this is what causes conductivity, okay? That's basically how we measure salts, is the amount of electricity that the sample will conduct. You guys ever done that experiment where you take like a beaker of water and you put 2 electrodes in it and, you know, maybe a light bulb in between? And as you add salt, the light bulb lights up. Have you ever done that before? Yeah, have you? Okay, so basically that's basically what it is if when you add salt, it conducts electricity, and that's how we measure salts in the soil. So the best way to represent this is, and kind of the effect that the salts have on a plant, is this idea of osmotic potential. And we talked about this earlier in the year when we talked about water movement. But what osmotic potential is that, let's say that out here in the bulk soil solution, we've got all these salts, and we're going to call sodium is going to be our salt in this case. The only reason that water moves into a plant is because within the root, there's more salt than within the bulk soil. Okay, but osmosis tells us what? If we've got more salt out here in the soil than we do in the plant, which way is the water going to flow? In or out of the plant?
In towards the plant?
Out.
Wow.
Because it wants to equilibrate, right? So if we've got less salt in the plant and more out here, water is going to move out here to try to dilute that salt. So it's the same concentration. So one of the telltale signs of high salt in a plant is that we get things moving out, or water basically moving out of the plant, and we can have dry, wilty looking plants. Maybe the leaf edges are burned a little bit. And that's despite the fact that there's plenty of moisture in the soil, but the salts are causing the moisture to flow the opposite direction. And that's because of osmotic potential. Does that make sense?
Yeah.
Yeah, that's really the only reason why water flows into a plant is because out here, generally speaking, we have less salt, more salt in here. And then after that, the water potential moves up through the plant, more salt up here, and then eventually out of the plant, which is a different mechanism. But it's basically a salt gradient from soil to root to plant tissue up here. Okay, so we measure salts with electrical conductivity, and there's a couple ways of doing it. We typically make an interpretation off the EC result from a saturated paste. So that's what this ECSP stands for. What a saturated paste is we'll take a soil sample and basically make a mud sickle out of it. And we suck the juice off of it. And we measure the electrical conductivity in that water that gets sucked out of the sample. So, that's the kind of standard for how we interpret electrical conductivity. In my lab and in a lot of commercial labs, what we'll do is we'll measure electrical conductivity on a 1 part soil to a 1 part water slurry. And then we multiply it by a factor to estimate what the saturated paste EC is. So some units to be aware of. Most of the civilized world reports electrical conductivity in millimos per centimeter. Okay, and then this is actually scientific notation down here. The other way of doing it is decisiemens per meter. The beauty of these two measurements is that if it's reported in micromos or decisiemens, it's actually the same number. So if you measure an electrical conductivity, and let's say it's a 4 millimos, then you can say that it's also 4 decisiemens per meter. It's the same number. Do you know where this mos comes from? Have I talked about that in class yet?
No, I don't think so.
What's that?
I don't think so. You told that.
Yeah, so everyone's familiar with ohms, right? We measure electrical resistivity with ohms, like an ohm meter. Well, the inverse of an ohm, the inverse of resistance is conductivity. And so they just spelled ohms backwards. So a mo is an ohm, the inverse of an ohm. Isn't that funny?
Yeah, it is.
Okay. All right. So again, with the saturated paste, what we do is we take the soil, mix it into a paste, and it's not like there's no standing water in it. It's just basically a mud sickle. Well, we put it under a vacuum with a filtration system, and the extract is drawn out, and then we run it through a conductivity cell. So in order to have salt accumulation, number one, there has to be a source of salts. Whoops, let me go back. There has to be a source of salts, and that could be from parent material, it could be from fertilizers applied, it could be manure, any of those things. It also tends to happen where we have a high water table. And the reason for that is if you have a high water table, you tend to have a lot of evaporation close to the surface. And when that happens, the salts get left behind. And also when we have poor drainage, we'll get an accumulation of salts. And again, when we have this evaporating that occurs at the surface of the soil, that's where we have a really high accumulation of salt. So that's exactly this is a crappy picture, but It generally happens that these salts build up right at the surface because that's where it's moving with the water up to the soil surface, it evaporates, and then those salts get left behind. So that brings up kind of a natural question is how do we get rid of this stuff, right? The easiest way to do it is by leaching, okay? Most of these salts are soluble, so they're going to move with the water. But in order to do that, you have to have good irrigation water. Some irrigation water is more salty than other. And so if you're trying to move salt down with water that's really salty, you're just going to be accumulating more, right? So you have to have good water. Also, you have to have good drainage. Okay, if you're trying to leach something and the water has nowhere to go, it's just going to puddle up and do nothing. So you have to have good drainage. The other option is you can live with it. So one thing that, this is fairly common down like in Southern California, like the Colorado River area. They have soils that have become, they're saline. So they've had a lot of salt accumulation over the years. And one of the things that they'll do is they'll either plant salt tolerant crops. Not all crops react to salt the same. And I think I've got a table on that in just a little bit. But what they'll do down in California is that they will plant on the side of the furrow. So let's say that you're irrigating with furrows. Here's your furrow right here. What they'll do is they'll plant their plant right here rather than on the top of the furrow, which is what most everyone else does. And those salts, again, are going to move to the highest point with the water before it evaporates off. So this area right here will actually be less saline than the area up here where they'd normally plant. So that's kind of one of the management practices that's used to deal with salts. Or you can just move too, right? If you have too bad a salt problem, it's kind of hard to get rid of, especially if you've got no way of providing drainage and you don't have good water. I mean, there's really nothing you can do. Okay, guys, this table right here, you need to memorize it. And it's so easy to memorize. Let me walk you through it. So when we're looking at a salinity class, we're paying attention to electrical conductivity. So let's look at a normal soil. A normal soil, this means less than, right? A normal soil is going to have an electrical conductivity less than a 4, okay? A saline soil, which has a high accumulation of salts, is going to be greater than 4. So more electrical conductivity tells us that it's going to have a higher salt concentration. So for now, that's all we need to remember. A normal soil, less than 4. A saline soil is going to be greater than 4. So let's look at a couple of salt-affected soils and let's determine whether these are high EC or if they're saline or they're normal. So let's look at soil A, okay? At the surface, we've got a 2.6. And as we work our way down, it's a 1.9, 1.3, and a 0.88. So this in its totality, what would you say? Is that normal, saline? What do you think? Remember, our cutoff is 4, right?
Yeah.
So everything's below 4. So this soil right here, in terms of salinity, we're going to say it's normal. Let's look at B here. We start out up at a 9.5, 5.8, and then we drop down to 1.9 and 1.3. So right here, we'd say that the 0 to 6 and the 6 to 12 inch sample, those are saline, right? Higher than 4. And then once we get below that, these would be normal. Okay. Freddie, you're going to do soil C. What can you surmise from this soil?
That said saline.
Okay, the whole thing,
Huh?
the whole thing.
No, just the top part.
Yeah, so the top 6 inches at a 15.8, that's definitely saline. And then the 6 to 12 at 6.58, yeah, definitely saline. And then after that, we're back into the normal range, right? Okay, Manish, what do you think about soil D?
So D is not normal every,
Right, so this one we'd call saline, right?
yeah.
The whole thing, because every one of them's got an EC greater than 4. So we're going to call this a saline soil. Okay, good. So we're going to move into kind of these two are often lumped together, but they're different problems, okay? In this case, we're going to talk about sodicity. Now, sodicity is a condition that is brought about because of one particular salt, which is sodium, okay? That's where this sodicity comes from, it's the word sodium, okay? And sodium, it behaves a little bit different than all of the other salt type elements, okay? And we've talked about this in class, right? You guys remember way back at the beginning of class when we did our texture analysis and we added that sodium hexametaphosphate? Basically what we did is we induced a chemical sodicity problem because we wanted all the different clay particles to disperse, okay? And so what we have is a lot of sodium that's causing a physical reaction in the soil. And what happens is that those individual clay particles push apart, and that can cause surface sealing and restrictive layers. And so what you'll often see in a high sodium situation is you'll see this cracking and stuff. And don't be led to believe that these cracks will let water infiltrate through them very fast, because they don't. This will infiltrate water extremely slowly. It'll pond. And so this makes our problem of getting rid of salt, and especially sodium salt, very difficult, because eventually we're going to have to leach this stuff out. But if the surface is sealed, how the heck are we going to do that? So sodium is very, very bad in the soil. You guys remember this calculation? You did this on your base saturation calculators. Just the exchangeable sodium divided by the CEC, okay? This is what we call ESP, and is one of the ways that we measure sodicity. The other way that we measure sodicity is with it's called SAR, so sodium adsorption ratio. And basically what this is it's the ratio of sodium, which is bad, to good stuff like calcium and magnesium. So SAR is commonly analyzed from the same extract that we use for electrical conductivity. So when we take that mud sickle, suck the juice out of it, we'll measure SAR on that. And this is what the equation looks like. Now, this is just for your information only. I'm not going to make you guys calculate this for this class, but that's what it is. It's basically a ratio of sodium to the square root of the average of calcium and magnesium. And somehow that works, okay? All right, I'm gonna just skip this part because I don't need you guys to calculate it in class, but if you ever want to go back and review, this is how it's done. Okay, we already talked about this, crop tolerance, crop management for saline soils. So let's go back to this table here. And for the time being, we just looked at these two right here, right? A normal and a saline soil. Well, let's now open it up and talk about a saline sodic soil and a sodic soil. And we're going to talk about these other parameters right here too, now that we know what they are. So ESP, this is our measure of exchangeable sodium. You'll notice that when we move into the world of saline sodic and sodic, that ESPs can be greater than 15. Below that, it could be saline or it could be normal. Same thing with the SAR. The SAR is identical, except we use a value of 13 as the cutoff. And then pH is also helpful. When we get into the world of a sodic soil, the pH is typically greater than 8.3. So if I gave you guys some examples, we could determine whether something's normal, if it's saline, saline sodic, or sodic. Okay, we'll do that in just a minute here. So in order to properly manage sodic soils, we've got to you have to develop a plan, because there are ways of getting rid of it, but there might be some things that get in your way. Okay, we have to consider leaching potential. Like I said, all this stuff's going to have to be leached out, and if we don't have any means for drainage or water movement, it's going to be really, really tough. Okay, and then we can determine chemical and organic amendments. I'll talk about these in just a minute, but it's a long-term management thing that we have to do. So for sodium, if our problem is specifically, let's forget about the total salts for the time being and the salinity problem. Let's focus on if it's just a plain old sodium problem. The way to get rid of it is that we need to replace that sodium with an exchangeable form of calcium. Okay. And the way we do that is with a product called gypsum. And this is what your walls are made of, right? The wall in the back is made out of gypsum. That's calcium sulfate. And so what that does is, let's say that we've got a clay particle here that's occupied by a bunch of sodium. We add the calcium sulfate, and our hope is that calcium will outcompete the sodium on those exchange sites, and then the sodium and the sulfate can be leached out. So that's basically the process, how it works. We've got to replace the sodium with an exchangeable form of calcium. There's a couple ways of doing it. As far as calcium sources go, you can use calcium nitrate, this calcite, dolomite, but gypsum by far is the most common. The reason being is that calcium nitrate tends to be very expensive. It's really soluble. That's what these numbers over here are, is the solubility factor on them. But gypsum is much, much cheaper. It's way more soluble than like dolomite or calcite. And so this is the product of choice. This also comes with a little bit of sulfate, which is an element that you guys know that plants can use. So gypsum's probably the way to go. The other way that we can do it is with elemental sulfur. Now, this might look like a bunch of mumbo jumbo to you, but let me kind of demystify it here. So what happens is we can add sulfur to our soil. That combines with oxygen, and the microbes turn it into this product called sulfite, okay? When sulfite combines with water, it forms this H2SO4. Do you guys know what that is? That would be sulfuric acid. Okay, so we're making acid here. Now, if we add acid to calcium carbonate, it's going to cause that to form calcium sulfate. Wait a minute, calcium sulfate? That's what we used right here, isn't it? Calcium sulfate. So basically, by adding elemental sulfur, we've caused the creation of gypsum. Okay, and then the reaction is the same after that. So we add calcium sulfate, it outcompetes the sodium, and then the sodium can be washed out. So kind of a longer term process, but it yields the same result. Adding elemental sulfur is going to cause us to create gypsum, and thereby we can leach out the sodium. Does that make sense? Might need to go back and look through this again, right? But it's kind of a cool way of doing the same thing. So there's a bunch of different sulfur sources. You know, we've got elemental sulfur, and then we've got things that are actually more, this is what we call like an equivalent ton. So sulfur, we call it a 1. And then there's other things that are actually more efficacious than just plain old elemental sulfur. But again, these things tend to be more more expensive. So you can add sulfuric acid, gypsum, but you have to add quite a bit more to get the same effect as 1 unit of sulfur. So looking at the amount of gypsum that we need to add in order to make a similar effect. So let's say that we add, and let's compare these bolded columns. So take a look at this column right here and this column right here. So if we want to affect, you know, 1 milliequivalent of sodium, it's going to take 1.7 tons per acre of gypsum and only 0.32 of sulfur. Okay. So the sulfur is going to be a little bit more efficacious than the gypsum. However, the gypsum is less expensive, so more people use gypsum than elemental sulfur to make this reaction. If we want to, you know, if the sodium is super high, we got to put on 8.6 tons of gypsum and only 1.6 tons of elemental sulfur. So you can see that, again, not as effective, more effective, but price is a concern. And so it's quite a bit, you know, if you have a lot of sodium in the soil, you've got to add a lot of gypsum to take care of that sodium. Okay, so I think this is the part where we're gonna review and maybe give you some examples, and we're gonna determine the salinity class. Okay. So remember, normal is less than 4, less than 15 and 13, and the pH is less than 3. If we've got a saline soil, we've got a high EC. Our sodium isn't necessarily high on these two parameters, and our pH is less than 8.3. If we've got a saline sodic soil, EC is high, so is the ESP and SAR, and the pH doesn't quite get affected yet. But on a sodic soil, our EC can be low, high sodium, and high pH. Let's try a few. Yeah. Develop a plan, go slow, be careful. I think I said this stuff already. A lot of this stuff I'm going to skip. It's more information than we need for this class. Okay. All right. Water quality. We got to be careful with sodium, right? And then and we're just talking about like irrigation water. So sodium in irrigation water is bad. Alkalinity and carbonates are bad. And the really bad players in irrigation water are sodium, chloride, boron, and bicarbonate to some extent. Okay, this is where I wanted to get to. So let's say that we've got a soil with a pH of 8.9. We've got an EC of a 2.3, and the SAR is 18. How would we classify this? Normal, saline, sodic. What do you think?
I think it'd probably be sodic.
Okay, why do you say that?
Because it has a greater pH than 8.3, and the SAR is greater than 13.
Yep, and our EC is 2.3. So that's less than 4. So we can confidently say this is a sodic soil. All right, Manish, you're up on the next one. What do you think on this one? pH is 7.4, EC is 5.7, and SAR is 2. I wonder if he stepped away. What do you think on this one, Freddie?
It might be saline, but Is it saline sodic or?
Well, to be sodic, right, we've got to have something greater than 13 right here, right?
Yeah.
So it can't be sodic. Our EC is high, right? It's over 4. So this is a plain old saline soil.
Okay.
Okay. And this last one, I'll do it. So we got a pH of 8.5. That's greater than 8.3. That's high. That's high. So this is probably a saline sodic soil right here. Okay, you guys get the benefit of being here today. I've got a trick question on the exam, on the final. So on the final, I think I've got a question that looks like this. So I give you the pH and I give you the EC, and that's it. I don't give you the SAR. And I even think that the EC that I give you is high. And I say, how would you classify this soil? Normal, saline, saline sodic, or sodic? And everyone says saline, right? Because this is high. But if you don't know the SAR, you can't tell if it's saline or saline sodic. It's one of the two, but you can't tell. You guys picking up what I'm putting down here? What if I gave you, that doesn't work so well the other way. Yeah, it's a good trick question. That's all I've got
For today.
for today. Yeah, what are your questions? Oh, let me, I'm going to stop the share here for a minute and get out of PowerPoint because I want to show you guys some of the different crops and how they react to salt, because they can be very, very different. Let me go here to the old Google. Share my screen again. Okay, can you see my Google there?
Yeah.
So let's go to soil. And it seems like, oh yeah, here we go. Stuff's out of Utah State. This is probably good stuff. Are they going to show me an example here? What the heck? Oh, here we go. All right. So we got some different crops listed here on this side. And there's a threshold value. And then they give the potential yield loss at 10%, 25, and 50. So again, this is EC. We learned about this right here, right? Decisiemens per meter. So look at barley, 8.0. If we had a EC in the soil of an 8.0, we'd call it saline, wouldn't we?
Yeah.
But barley, you can go all the way up to an 8 without having any yield loss. Okay. Once you get up to like a 9.6, then you're starting to see yield loss, a 13 and a 17. But barley is the prime example of a salt tolerant crop. Does very well. Let's look at beans. What if we've got an EC of 4 and we call that normal, right? Or let's say it's a 3.5. Okay, that's normal. But beans, anything above a 1.0, you're going to start to see some yield loss. So 10% at 1.5, 25% at 2.3. And then we haven't even got to 4 yet. And you're seeing like a 50% yield loss on your beans because of salt. So can you guys see that good enough that crop makes a huge difference in salinity? If you've got really saline ground, yeah, maybe you're growing barley. You're not going to try to grow beans, that's for sure. And if we got some other ones here. Bermuda grass, it's pretty tolerant. What's something that's not very tolerant? Clover. Do they have potatoes on here?
Right there.
Yeah, potatoes are pretty sensitive. Peas are too, 0.9. Okay. So yeah, you might have to keep that in mind when you're growing stuff, that if you're in an area with a lot of salt, you have to be careful about what you're growing. Manish, what's the salt like in Nepal? You guys get areas with salt?
No, not really.
Not really? Okay.
No.
Yeah, this is a good resource right here. Okay. So on Monday, and I'll send out an announcement, I want to do one last lecture, I'm pretty sure. So we'll probably do it on Zoom, unless I find something really good to share with you. I want to talk about erosion. That's something that we haven't covered yet. So anyway, be looking for that on Monday. And then, yeah, good luck on your fertilizer calculations. If you guys want to work on them together, I have no problem with that. Because I think it helps when you get other ideas and instead of just struggling with it on your own. But yeah, that's a pretty tough assignment. You guys can do it. It's not so hard that you can't.
And then we have a quiz tomorrow, right?
Yep. Okay, that's all I got. We'll talk to you guys soon.
All right. See ya.
See ya.
See ya.